All right, before we start, the chemistry department has asked us to announce that we have scholarships sponsored by the department and the college. And the deadline for applying for those is April 12th. I think that's about 2 weeks from now. So go ahead and take a look at this website. It's from the chemistry. There's a link to it on the chemistry department website that'll give you more information about the types of scholarships, how you would apply for them, what the qualifications are. But I encourage you to apply because we want you to take advantage of these resources that we have. And then, of course, the paper is due. So most of you have turned those in. If you've come in and you haven't, make sure you turn it in on your way out. Another announcement we have is that we will have our next quiz on Wednesday. And this is our second extra quiz. So this is the second one that you'll be able to replace a lower quiz score. So make sure you are up to date in your reading and studying, so you're ready for that. So on Friday, we introduced monosaccharides, and we talked about the cyclic hemiacetal form of the monosaccharide that is the dominant form. Today, we're going to continue our discussion of cyclic hemiacetals, and then we're going to start talking about reactions that monosaccharides can undergo. So we showed you how to convert from a Fisher projection to a Haworth projection, and we showed you about anomers, the alpha anomer, where the hydroxyl at the anomeric carbon is trans to the primary alcohol, and the beta anomer, where that hydroxyl at the anomeric carbon is cis to the primary alcohol. What we didn't tell you yet is that there is an equilibrium between these anomers. They interconvert with each other, okay? And they interconvert via the acyclic aldehyde form. So this slide here shows you the equilibrium with glucose. At equilibrium with glucose, you'll have less than 1% of the acyclic aldehyde and more than 99% of the two anomers. But the formation of the cyclic hemiacetal is reversible. We learned the mechanism back in chapter 21. We discussed it on Friday. But you can take your anomer here. You can protonate this oxygen. Then you can cleave this carbon-oxygen bond and then deprotonate that oxygen. Those three steps will get you back from the cyclic hemiacetal to the acyclic aldehyde form. So that's a reversible process. And then when you reform the cyclic hemiacetal, you could reform either the alpha or the beta anomer. Okay? So this process of converting one anomer to the other via the acyclic aldehyde is known as mutarotation. Okay, interconversion of anomers is called mutarotation. Okay, so that's just a vocabulary word we need to learn. Okay, so another thing that you'll notice from this slide here is that the beta anomer of glucose is more stable than the alpha anomer of glucose. We get almost a 2-to-1 ratio of those two anomers at equilibrium. This is not general for all monosaccharides. This is only the case for glucose. It's different. This equilibrium is different for the different monosaccharides. Okay, so don't memorize that beta is always more stable than alpha. It is not. It's a complicated issue, so we're not going to get into it. But for glucose, it is true. The beta anomer is more stable than the alpha. And in a few moments, we'll actually see why that is the case. Okay? But please don't overgeneralize that and think that it applies to other sugars. Okay? So we learned how to convert a Fisher projection into a Haworth projection, one of these flat cyclic hemiacetal structures. And your book gives you kind of a shortcut method for doing this that's a little shorter than the one we learned in class. And we're showing you this with mannose. The first thing you want to do is draw your flat hexagon and put the ether oxygen in the back right corner. It's always easier to draw this draw these if we always put the ether in the back right corner. If we do that, if it is a D sugar, then the primary alcohol is always going to be pointing up when we draw the Haworth projection. We know it's a D sugar if in the Fisher projection, the OH at C5 is pointing to the right. Okay? Any questions on how we put that primary alcohol in place? Okay? So once we've done that, the next thing we're going to do is look at the anomeric carbon. And we will orient the OH group of the anomeric carbon depending on which anomer we've been asked to draw. If we've been asked to draw a mixture of anomers, then we would draw both. Remember, alpha has the OH group cis to the primary alcohol. So if it's a D sugar, that OH is always going to be pointing down in the alpha anomer. If it's beta, that OH at the anomeric carbon is cis to the primary alcohol, always going to be pointing up if it's a D sugar. Okay? And so now we just have 3 more stereocenters to fill in. And if you'll remember the process we went through on Friday, we rotated 90 degrees about C5, and then we rotated the entire Fisher projection 90 degrees clockwise. We put it on its side. Okay? And so when we do that, when we put it on its side, the substituents that are on the left are going to end up pointing up. The substituents on the right of our Fisher projection are going to end up pointing down. Okay, so we would just see, okay, in this monosaccharide, C2 is on the left, OH, C3OH on the left. Those 2 OHs have got to be pointing up in our Haworth projection. C4OH is pointing right, that's going to be pointing down. So we go up, up, down, filling in our alpha anomer, up, up, down, filling in our beta anomer. Okay? Any questions on how we drew those Haworth projections from the Fisher projection? So this monosaccharide, we told you over here it was mannose. How does mannose differ from glucose? Has anyone studied the connection between mannose and glucose yet? I hope someone has. Yes, Brady? It is the C2 epimer. Okay, so mannose and glucose only differ at C2. Glucose goes right, left, right, right. Mannose then goes left, left, right, right. Okay, so glucose would have this OH group pointing down. And remember, the beta anomer of glucose alternates up, down, up, down, up. And so mannose is just the epimer at C2. Okay? So in addition to being able to convert a Fisher projection into a Haworth projection, we need to be able to go in the opposite direction. We need to be able to take a Haworth projection and convert it into a Fisher projection. And that's what this sample problem shows us. So the first thing we want to do is look at our primary alcohol. Well, actually, the first thing we want to do is draw our aldehyde and our primary alcohol in the product. Okay, we know that the aldehyde is going to be at the top, primary alcohol is going to be at the bottom. Second thing we do is determine if it's a D sugar. How do we determine if it's a D sugar from the Haworth projection? The primary alcohol is pointing up. The primary alcohol is pointing up. It's a D sugar. So then in the Fisher projection, we stick the C5OH on the right. Okay? So now we just have to fill in C2, C3, and C4. So to go from Fisher to Haworth, we rotated 90 degrees clockwise. To go from Haworth to Fisher, we therefore would rotate 90 degrees counterclockwise. We take our Haworth projection, and your chair is having problems, I guess. Sorry about that. We rotate that Haworth projection 90 degrees counterclockwise, and we see that any OH group that's pointing down is going to end up on the right. Any OH group that's pointing up is going to end up on the left. Okay? And so C2 pointing down on the right, C3 and C4 pointing up, those end up on the left. Okay? Any questions at how we go from the Haworth projection to the Fisher projection? Any ideas? Any questions? Okay. So, can anyone tell me which monosaccharide this is? It's one of the, I'll give you a hint, it's one of the ones we need to learn. So if you don't know it now, yes, it's galactose, okay? Galactose is the C4 epimer of glucose. Only differs at C4, okay? All right, so now we know how to go back and forth between Fisher projections and Haworth projections, but neither of those represents the three-dimensional shape of a monosaccharide, especially an aldohexose, when it's in solution. How would we need to draw glucose or one of our other aldohexoses if we wanted to draw what it looks like in solution? As a chair, exactly. We would need to draw the chair conformation. So we need to figure out how to go from a Haworth projection to a chair conformation. We're going to show you how to do that here on the board. So the tricky thing is that you've got your two different chair conformations that interconvert by ring flipping. So you've got more than one way that you can draw the chair of a pyranose or a six-membered cyclic hemiacetal. But there's one way to draw it that's going to make it much easier for you, and that's the way I would recommend. So remember, in the Haworth projection, we're putting that ether oxygen in the upper right. So we want to draw the chair conformation that does the same thing. Okay? So notice how I put that ether oxygen in the upper right so that it corresponds to the same position where we put it in our Haworth projection. Okay? So the next thing we'll do is we'll draw in our equatorial groups. And remember that in a chair, each equatorial bond is supposed to be parallel to two bonds in the chair conformation. Okay? And then we need to draw in our axial bonds. Those are going to be pointing either straight up or straight down. Okay? Now we put the groups in position. Right? If we have the oxygens in the same place, all we have to do is transfer the groups that are up in the Haworth projection to up positions on the chair and do the same thing with the ones that are down. So let's look at our primary alcohol. That's pointing up. So we put that up over here, and that ends up equatorial. The alcohol at C4 is pointing down. We put that here. That's also equatorial. The alcohol at C3 is up. That ends up equatorial. The alcohol at C2 is also up. Or down, sorry. The alcohol at C2 is down. Goes equatorial. And then the anomeric hydroxyl is pointing up. Okay? Any questions on how I filled in those groups? Okay, and now we'll put the hydrogens in. We don't always have to draw the hydrogens, but we'll draw them this time. And what do you notice? Do you notice something about this, the beta anomer of glucose? Yes, Grace. Okay, all the hydrogens are axial, all the alcohols as well as the primary alcohol are equatorial. So now we know why the beta anomer of D-glucose is more stable than alpha, because it has all of the groups equatorial. Okay? That's not the case with other carbohydrates. Other monosaccharides would have one or more OH groups axial. Okay? So if you draw the chair in this form, then with that ether in the upper right position, it's very easy to transfer from the Haworth projection to the chair conformation. So this is glucose. To draw the other aldohexoses we need to know, mannose and galactose, my suggestion is just to memorize the difference between those monosaccharides and glucose. Okay? So we know that beta D-glucose is going to have all the groups equatorial. Okay? So if we have to draw beta D-mannose, we need to change which carbon? C2. So we would go to C2. If it was mannose, we'd put the OH at C2 in the axial position. Which one would we need to change if it was galactose? C4, which is over here, that one would be axial in galactose. Okay? So if we're drawing the chairs, I recommend just memorizing the differences from glucose, noting that glucose is going to have all of them equatorial if it's the beta anomer. Of course, if it's alpha, the anomeric hydroxyl is axial. And just switching the stereocenter that is different from glucose if you've been asked to draw mannose or galactose. Any questions? All right, so we also need to look at the 5-membered cyclic hemiacetals, known as the furanose form. Those are more common with pentoses, with ribose, for example. And your book actually tells you or implies that for ribose and other pentoses, that the 5-membered cyclic hemiacetal is more stable than the 6-membered hemiacetal. That is not true. That is not correct. Okay? Let's take a look at this figure right here. This shows the actual equilibrium. Here's ribose. Open chain form less than 1%. We can form pyranoses from ribose because we only have 5 carbons. To do so, we have to use the primary alcohol, the alcohol at the end of a chain. But we do form those pyranoses. And as you see at equilibrium, about 75% is going to be in the pyranose form. And about 25%, so pretty much a 3-to-1 ratio, favoring the pyranose over the furanose. To make the furanose, the 5-membered cyclic hemiacetal, we're using the secondary alcohol, the one shown in blue. Okay? So why does the book tell you that the furanose dominates when it doesn't? Well, the reason is that the furanose form is the one that is more relevant in biochemistry. Okay? If you were to just dissolve ribose in water, this is what you would get. But if you have ribose as part of RNA or other pentose derivatives as part of DNA, this is what you get. You get the furanose. Okay? And there's a reason for that. When you form the furanose, you have a primary alcohol. When you form the pyranose, you don't have a primary alcohol. And you need that primary alcohol to generate the phosphodiester backbone that you have in RNA and that you have in DNA. Okay? So when the most common place to see ribose and deoxyribose doesn't have this OH group at C2. The most common place that we see those in nature is as part of DNA and RNA. And when they're in DNA and RNA, they do indeed form the furanose. Okay? So the furanose is the most biologically relevant form of ribose, but it is important to know that the pyranose is actually more stable. Any questions? So if we were drawing a pyranose of ribose, we would draw the chair like this. But usually we will draw it in the furanose form, the 5-membered ring, because that's the form that's relevant in biochemistry. And the 5-membered rings, we draw those in the Haworth projections. We learned back in chapter 4 that 5-membered rings, they don't form chairs. They form 2 conformations similar to chairs. One is called the envelope and the other is called the half chair. Those are a lot harder to draw than chairs. Okay? And so we don't ask you to draw envelopes or half chairs. I even have a challenge drawing them. I usually have to look at a picture of one before I can draw it. So when we draw the 5-membered rings, we're just going to draw them flat in these Haworth projections. Okay, so even though they're not flat, we're still going to draw them in this way. And when it's a 5-membered cyclic ether, we're going to put the ether in the back in this fashion. That's going to make it easier to draw. Okay. So we're just going to show you on the screen how to go from the Fisher projection of ribose, or any other pentose for that matter, to the cyclic hemiacetal form, the furanose form. Okay, because it's going to be basically the same as what we did on the board on Friday for the hexoses and the pyranose forms. Okay, so the first thing we're going to do is we're going to rotate 90 degrees about this carbon right here. That's going to put this oxygen down. That oxygen is going to now be linear with the aldehyde, and that's going to move the OH, CH2OH over here. Then we're going to rotate 90 degrees on its side. That's going to put the groups on the right down, the groups on the left up. Then we're going to cyclize using that blue alcohol, that secondary alcohol at C4, to make our hemiacetal. So if it's a D sugar, the primary alcohol being over here is going to end up, right? So we draw that primary alcohol up in both cases. We fill in the anomeric carbon. If we're asked to draw the beta anomer, anomeric OH, cis to the primary alcohol, are pointing up. If we're asked to draw the alpha anomer, the alcohol is going to be trans to the primary alcohol, pointing down. Now all we have left to do is fill in C2 and C3. In ribose, remember, all the OH groups are on the right. So when you rotate that 90 degrees, the groups on the right end up down. So at C2 and C3, the OH groups are pointing down. Any questions about how we would draw the furanose forms of ribose using these Haworth projections going from a Fisher projection? Any questions? Okay then, so make sure you practice this. We have a final type of monosaccharide that we need to be able to draw in its cyclic hemiacetal form, and that is a ketose. Okay? So what is the ketose that we needed to learn the structure of? Which ketose did we need to learn? Yes, fructose, exactly. Okay? So we're going to show you how to draw fructose in the cyclic hemiacetal form. So first we'll draw our Fisher projection of fructose. Being a ketose, it has a primary alcohol at C1, and it has a ketone at C2. I kind of cringe when we draw the ketone in a Fisher projection because it's drawn flat. It doesn't show the bond angles correctly, but that's what we're stuck with. So just remember, it doesn't represent the actual conformation. But then remember that fructose is identical to glucose at all of the stereocenters it retains. Glucose goes right, left, right, right. So that tells us that C3, C4, and C5 have to be left, right, right in fructose. Okay? And then we fill in our other groups. Okay? All right. So the first thing we do, we rotate 90 degrees about C5 to put the secondary alcohol in line with our carbonyl. And then that moves the primary alcohol over here. And then remember, we're going to combine two steps here because we did them separately on Friday. Then we're going to rotate the whole thing 90 degrees clockwise. Okay? We're going to put it on its side in preparation for that cyclization. Okay? That's going to give us something looking like this. Okay, so this is C2, C3, C4, C5. So it's C5 because it's a D sugar. This primary alcohol is pointing up. Okay. And then at C3, this alcohol is on the left, so that's going to end up. Okay. And then at C4, that alcohol is on the right, that's going to end up down when we rotate 90 degrees. Okay. And now we're going to fill in our hydrogens. Okay. Any questions on how we went from here to here? Okay, so now we're going to cyclize. We're going to end up with a mixture of anomers. We'll draw one up here. So we're forming a 5-membered ring. We're going to draw it like this with the oxygen in the back in the Haworth projection. We keep our OH groups like this. Okay, so now we're going to draw the anomeric carbon. If we're drawing alpha, that OH is going to be trans to the primary alcohol. But here's the difference between a ketose and an aldose. An aldose has a hydrogen on the aldehyde, and that hydrogen ends up in the anomeric carbon. A ketose has no hydrogen on the ketone, and so the anomeric carbon has no hydrogen attached. Okay? This is our anomeric carbon. It bears the OH, and it bears the primary alcohol. Okay? So the anomeric carbon of a ketose looks different than the anomeric carbon of an aldose. Okay? How do we recognize the anomeric carbon? How do we spot it in a monosaccharide, in a cyclic hemiacetal? There's an easy way to spot the anomeric carbon. It has a unique property compared to all the other carbons. So every carbon of a monosaccharide, of a normal monosaccharide, has at least one oxygen attached. But how many oxygens are attached to the anomeric carbon? 2, exactly. The anomeric carbon is the only carbon in a monosaccharide with 2 oxygens attached. So that's how you spot it in a monosaccharide. So this one is alpha D-glucofuranose. And then we'll draw the beta anomer down below. As I'm drawing this for you, your book also tells you that the furanose, or the 5-membered ring form, dominates for fructose. That is also not correct. Okay? You can draw a pyranose, or a 6-membered cyclic hemiacetal, for fructose. And indeed, that 6-membered cyclic hemiacetal is more stable than the 5-membered cyclic hemiacetals. Not by as much as it is for ribose. In ribose, it's about a 3-to-1. It's about 75 to 25. In fructose, it's about 60-40. 60% of the pyranose, or the 6-membered cyclic hemiacetal, about 40% of the 5-membered. Okay? But as is the case with ribose, it is the 5-membered form, the furanose form, that is more relevant in nature and more relevant in biochemistry. When we link fructose to other monosaccharides to make disaccharides or polysaccharides, we're going to do so using the 5-membered form. Okay? So if you dissolve fructose in water, you'll get more of the 6-membered cyclic hemiacetal than the 5-membered. But if you are seeing fructose as part of a polysaccharide or a disaccharide, which we'll talk about starting on Wednesday, you'll see it in the 5-membered form. So we'll typically draw the 5-membered form, the furanose form, even though it's slightly less stable than the 6-membered form. Any questions? All right, so make sure you practice this. Make sure you are able to draw monosaccharides in their various forms and interconvert those forms without messing up the stereochemistry. Now we're ready to talk about reactions of monosaccharides. So we have multiple functional groups in a monosaccharide. Therefore, we have multiple reactions that can occur. There are 3 places that we can see reactions of monosaccharides. One is at the hemiacetal, or the anomeric, either the anomeric carbon or the OH at the anomeric carbon. Okay, that's one place we can have reactions of monosaccharides. We can also have reactions that occur at the hydroxy groups. We've learned a lot of reactions that occur with alcohols. Some of those will work with carbohydrates, others will not. And we'll talk about both cases today and on Wednesday. And then we can also have reaction at the carbonyl group. You might say, wait a minute, there's no carbonyl group in these cyclic hemiacetals. That is true, but we have an equilibrium, meaning that at any given time we have a little bit less than 1% of the open chain aldehyde or ketone, depending on if it's an aldose or a ketose. So if we perform a reaction at the carbonyl group, such as a reduction or an oxidation, we can react the slightly less than 1% that's existing at equilibrium, and then according to Le Chatelier's principle, the equilibrium will adjust to make more of the acyclic aldehyde or ketone. So in this way, using Le Chatelier's principle, we could convert all of the monosaccharide into a product by a reaction at the carbonyl group, even though we would only have a small amount of that carbonyl group present at any given time. Any questions about that? Okay, so 3 types of reactions. We'll get into all 3, but we're going to start with a reaction that occurs at the anomeric carbon, at the hemiacetal of a monosaccharide. Okay, this reaction is going to be called glycoside formation. Okay. So we're going to use glucose as our example for glycoside formation. It doesn't matter which anomer we draw. We'll just go ahead and draw the alpha anomer in this case. And when we make a glycoside, we're going to react our monosaccharide with an alcohol in the presence of a strong acid. Okay? So we'll use methanol, our simplest alcohol, just to show the products that we get and to draw the reaction mechanism. And then we'll use HCl as our acid. So what will happen in this reaction is we are going to replace the anomeric hydroxyl with an ether, okay? But only the anomeric hydroxyl. We're not going to make ethers from any of the other alcohols, okay? Those are going to remain as alcohols. And it doesn't matter which anomer we start with. In fact, we always have to start with a mixture of anomers. There's no way to have just alpha D-glucose or beta D-glucose. We always have that 2-to-1 mixture. But as you'll see when we draw the mechanism, even if we were able to have a single anomer, even if we were able to start only with alpha D-glucose, we would get a mixture of alpha and beta glycosides, okay? So we still use the same alpha and beta terminology when we're talking about glycosides. So glycosides are ethers at the anomeric carbon, which means that this functional group is now called an acetal. A hemiacetal has an ether and an alcohol attached to the same carbon, whereas an acetal has 2 ethers attached to the same carbon. So converting a hemiacetal to an acetal is converting a monosaccharide into a glycoside. A glycoside is an acetal at the anomeric carbon. And so this would be alpha and this would be beta. Okay? All right. So we're going to draw the mechanism of this process. We'll draw it over here on our sideboard. And when we draw it, you'll see why it doesn't matter which anomer we start with, we would get a mixture of both glycosides, anomers, even if we could choose a single anomer to start with. Okay? So just to prove that point, let's draw beta D-glucose instead of alpha D-glucose, and we'll see that we get the same outcome. All right, now we've seen a whole host of reactions throughout the year involving alcohols reacting with acid. What happens when you treat an alcohol with a strong acid? You protonate the oxygen. Well, we have a whole bunch of alcohols to choose from in our monosaccharide. So which one do we protonate? The answer is we can protonate any of them. But only one of them is going to lead to the glycoside, and that is the anomeric hydroxyl. Okay? So when we're drawing the mechanism, we're going to protonate the anomeric hydroxyl, recognizing that we can protonate any of these hydroxyls, but that protonation is reversible. And protonating those other hydroxyls is going to be a dead end, as you'll see in a moment. Okay? So let's draw the product we get when we protonate the anomeric hydroxyl. It's going to look like that. We'll draw in our other OHs. Okay, so going back, drawing on our knowledge of reactions of alcohols, what happens next after we protonate the alcohol? It leaves. We lose water. Okay? So indeed, that's what happens here. We lose water. Because we're losing water from the anomeric carbon, we're losing water from a hemiacetal, we can actually use the adjacent oxygen, the electrons on that adjacent oxygen, to displace the water. Okay? And so we generate a cation, but because we've generated the cation at what was the anomeric carbon, it is a resonance stabilized cation. The positive charge can be shared by the anomeric carbon and the neighboring ether oxygen. But the major contributor of that resonance stabilized cation is the one that has the positive charge on the oxygen. So that's the one we will draw. Okay? So we've learned that, according to Hammond's postulate, more stable carbocations are formed more rapidly. We could protonate any of the alcohols in our monosaccharide, but only one of those protonated alcohols could lose water to generate a resonance stabilized cation. So this cation is formed much more rapidly than any other cation that you could form by protonating any of the other OH groups. Okay? So we protonate any other OH group, nothing's going to happen, the proton's going to come back off. We protonate the anomeric OH group, we lose water because we get this resonance stabilized cation. Any questions? All right, so now we have this resonance stabilized cation. Now is where the methanol comes into play. How is our methanol going to react with our resonance stabilized cation? Okay. We won't do acid base, we'll act as a nucleophile. We're going to attack the anomeric carbon. Okay? We attack the anomeric carbon, push the electrons back up into the oxygen. Is the methanol going to attack the anomeric carbon from the top or the bottom? Both, right? This is planar. This is an sp2 carbon. It is planar. So the methanol is going to approach from the top and the bottom. That's how we end up with both anomers of our glycoside, regardless of which anomer we start with, because we go through this intermediate cation where the anomeric carbon becomes planar. Okay? So we're going to get two anomers of the product. Let me draw that chair a little bit better. Okay. So here's the beta, and then we'll draw the alpha over here. I'm going to move that positive charge so it's not by that other oxygen. One of the challenges of drawing carbohydrates is you end up with a lot of functional groups in close proximity to each other. So it's a challenge to draw them. All right, so we've got the beta anomer and the alpha anomer, but we have the conjugate acid of our glycoside. So what's our final step that we're going to do in the mechanism? We're going to have to deprotonate that, and we can just use our chloride, the conjugate base, a very, very weak base, but the conjugate base of our acid. Since I'm out of space on the board, I'm only going to show the deprotonation on the beta anomer, but the same thing would happen to the alpha anomer. We'll just show it here with making the beta. And we've reformed HCl. Okay. Any questions about forming glycosides? One key thing to note about glycosides is that they do not undergo mutarotation. The glycoside is not in equilibrium with the open chain aldehyde. Okay? So there's no mutarotation. Once you have the alpha and beta anomers, then they're going to be stuck as the alpha and beta anomers. Okay? But you're always going to generate both because your alcohol is always going to attack from the top or the bottom. But if you could separate those anomers, they would not interconvert or equilibrate with each other. Okay? Question, Brady? No, there will be different ratios that will differ for each carbohydrate. So we're not going to get into that. We're just going to recognize that in each case, you're going to get both. But the ratios are not going to be one-to-one. They'll vary slightly depending on the type of carbohydrate. So we've drawn equilibrium arrows here. This is a reversible process. If we want the glycosides, we're going to use an excess of methanol. If we want to hydrolyze the glycosides and convert them back into the original hemiacetals, what would we use instead of methanol? If we want to convert the acetal back into a hemiacetal, we would need water. So we would use aqueous acid. Typically, we just write it as H3O plus and water. Okay. And to save time, I'm going to draw a squiggly line at the anomeric carbon, saving time and space. The squiggly line is another way of indicating a mixture of epimers at that particular carbon. So this squiggly line means we have both alpha and beta. Okay? So since glycoside formation is reversible, the reverse mechanism, or the hydrolysis of the glycoside, is simply the opposite of the mechanism we drew on the board. So instead of drawing it on the board, we're just going to look at the screen. Okay, we protonate. We can protonate any of the oxygens in our glycoside, but only if we protonate the ether at the anomeric carbon can we then lose our alcohol, which is methanol in this case, to generate the resonance stabilized cation. Right? There's only one resonance stabilized cation we can form. We're forming it in exactly the same way as we did in the forward direction. We're just using the alcohol, which is methanol in this case, as the leaving group as opposed to water. And then the other difference is we're using water as the nucleophile. And so the water is attacking that cation either above or below. The book is showing it from the minor contributor. You can show the minor or the major contributor. It doesn't matter. Giving us our mixture of anomers. And then we just use water as the base to do the final deprotonation. Any questions about that mechanism? So glycosides are common in nature. Here's a couple examples. Salicin is a naturally occurring painkiller present in willow bark. It was the inspiration behind the development of aspirin. We talked about that back in chapter 2, way back at the beginning of the year. Aspirin has a carboxylic acid here and an ester there and doesn't have the glycoside. But you see salicin has glucose here. And then digoxin, which is known as a cardiac glycoside, that's a heart medication. It has this trisaccharide attached to a steroid nucleus. You can see that it's an unusual, these are unusual sugars because they have methyl groups. They're called deoxy sugars. We'll talk more about those later on in the week. Okay? And any disaccharide or polysaccharide is also a glycoside. That's something we'll talk about more on Wednesday. But the next thing we're going to talk about is something that's in the book, but not in the chapter. It's in a homework problem, but it's a more important topic, in my opinion, than the book gives it credit for. So we're going to talk about it in class here. And this is what happens when you treat a monosaccharide with a strong base. Okay? So first thing I'll do is ask you, what reaction have we learned for making ethers? Way back in chapter 9. Williamson ether synthesis, exactly. So to perform a Williamson ether synthesis, we need an alkyl halide and what else? We need an alkoxide, which we use by deprotonating an alcohol with a strong base. So if we were going to perform a Williamson ether synthesis, if we wanted to make ethers of the other OH groups in our monosaccharide, we might want to try a Williamson ether synthesis. That would involve treating our monosaccharide with strong base. The problem is, lots of stuff can happen when you treat a monosaccharide with a strong base. So we'll just show glucose here. We're actually going to draw out the aldehyde here as opposed to showing it like that. Okay, so let's treat glucose with a strong base like hydroxide. We've got a lot of choices. We've got a lot of OHs that we could deprotonate. But we can also deprotonate this hydrogen. Why? What do we get if we deprotonate that hydrogen? We get an enolate. Okay, that's an alpha hydrogen. So we're going to form an enolate. Okay, this is what the enolate's going to look like in Fischer form. Okay, so we form the enolate. We don't form it completely because of the pKa of the aldehyde versus the pKa of water. But we're going to form some enolate and we're going to form some water. The water can then protonate the enolate. It's going to protonate back at the alpha carbon, C2 in this case. Is it going to protonate from the top or the bottom? Both, right? It's planar here, so we can protonate from the top or the bottom. If you protonate from one of those two faces, I don't actually know which one, but one of those two faces would give you back the glucose that you started with, okay? But if you protonate from the opposite face, you're not going to get glucose. You're going to get the C2 epimer of glucose, which is what monosaccharide? Mannose. Yeah, you're going to make mannose. We're going to switch the configuration at C2. Okay? So if you treat glucose with a strong base, you're going to get a mixture of glucose and mannose. But wait, there's more. That's not the only thing that happens. Okay? There's something else that can happen to the enolate that you generated. Okay? So we'll draw that enolate over here. Okay. So here's the enolate. Same thing right here. We can protonate it, but not on carbon. We can protonate on the oxygen, and that's going to give us an enol. Okay? If we protonate an enolate on oxygen, we generate an enol. Okay, only this enol is special because it's an enediol. It's an enol that has two OH groups attached to the alkene as opposed to just one. Okay? So we have this enediol. We protonated it with water. We generate hydroxide in the process. Okay? The hydroxide can deprotonate It could deprotonate the OH that just got protonated, or it can deprotonate this OH, generating a new enolate. Okay. Now that we have this new enolate, we can protonate that with water on carbon 1. Okay. If we protonate that enolate on carbon 1, we now end up with a carbonyl at carbon 2 and a primary alcohol at carbon 1. So which monosaccharide have we generated? Well, I'm drawing it here. Hopefully you can figure it out. We've made fructose. Yes. Okay. I wouldn't say yay. Usually you don't want to make 3 different monosaccharides from 1. Usually we like reactions that give you a single product. Okay. So if you treat glucose with a strong base, you're going to get a mixture of glucose, mannose, and fructose. If you treat mannose with a strong base, you're going to get a mixture of glucose, mannose, and fructose. If you treat fructose with a strong base, you're going to get a mixture of glucose, mannose, and fructose, okay? Because these are all equilibrium arrows. It's a reversible process, okay? This is a problem. You don't want 3 different monosaccharides. You want just the one you started with, typically. So the take-home message from this is that we cannot perform a Williamson ether synthesis on a monosaccharide. You're going to get mixtures of those monosaccharides. So if we want to make ethers at the hydroxyl groups other than the anomeric carbon, we need an alternative to the Williamson ether synthesis. We need another reaction. And that's where we're going to start on Wednesday. Please turn in your synthesis assignment if you have not done that already. And remember, we have a quiz on Wednesday.